Hello, so this video carries on from what we were doing in the last video which I've posted on the stream, which is all to do with moments. So it's the second part of moments. In the last video I introduced a moment and how to work it out. So in this video I'm going to look at a few examples on resultant moments, just carrying on from what we did yesterday, and then I'm going to look at moments in equilibrium, and then next lesson we can move on to looking at centre of mass and some at an angle, at different angles. So this first example that we're going to look at, okay, it's one of the questions from the textbook. So it says the diagram shows a set of forces acting on a light rod. So this is your light rod here. The resultant moment about P, so that's using P as the pivot, so P is where we're going to measure our moments from, is 17 Newton meters clockwise. Okay, find the length of D. So what we need to do is use the information in the question to come up with the clockwise moments, the anti-clockwise moments in terms of D, and then we can use the fact that the resultant moment is 17 Newton meters to find out what D is. So if we look, if P is here, okay, if I was to, if this force was to act on it, P would lift this rod up in the clockwise direction, so that anti-clockwise direction, so that 2 Newton force is an anti-clockwise, ignore me totally, clockwise direction, the last bit of the clock. Okay, in the same way, this 5 Newton force would also pull the rod in the clockwise direction if you look at my cursor there. Okay, the 4 Newton force, if we were to pull it downwards, okay, then this rod would start going like this, okay, so it would be in the anti-clockwise direction. Right, so now looking at our moments in the clockwise direction, okay, what we've got is for the 5 Newton force, we've got the distance, which is 3 times the force, which is 5, so we've got 3 times 5. And then for the 2 Newton force, we've got a distance of 5 from this 3 and 2 plus D times by 2. So we've got 15 plus 2 lots of 5 plus D in the clockwise direction. In the anti-clockwise direction, we've got a distance of 5 times 4. So in the anti-clockwise direction, we've got 5 times 4. So now, because we know that the resultant moment is 17 Newton meters clockwise, if we assume clockwise is positive and anti-clockwise is negative, we know that this 3 times 5 plus 2 lots of 5 plus D, take away 20 from 5 times 4 has to be equal to 17, so we can set up that equation. Okay, so considering clockwise is positive, anti-clockwise is negative, you've got 15 plus 10 plus 2D minus the 20 is equal to 17. So simplifying that now gives me 5 plus 2D equals 17, and then subtract 5, divide by 2, and it tells us that D has to be 6, so D is 6 meters. Okay, so that's the first one I'm going to talk through. The second example I'm going to talk through, this is a lamina, okay, which is like a rigid sheet, okay. So on this one we've got a lamina with 2 forces acting on it, and I know I've not put the question, but it wants to know the resultant force and the direction. So P is the pivot part of the lamina, okay, or a corner of the lamina. So if you picture which direction these 3 Newton and 5 Newton forces are going to act in, are going to turn the lamina. If we think of the 3 Newton force, okay, it's going to pull it up in this direction, so it would move in this direction, which is anti-clockwise. So the 3 Newton force would move it anti-clockwise, whereas the 5 Newton force, if we were to start pulling here, would move it in this direction, which is clockwise. So you've got the 3 Newton force is anti-clockwise, and the 5 Newton force is clockwise. It doesn't matter that they're acting in different directions or that it's a lamina, we treat it in exactly the same way. So now for our clockwise moment, okay, we've got the distance from P, which is 2, times the force, which is 5, and they're at right angles to each other, so you've got clockwise is 2 times 5, anti-clockwise, okay, we've got the distance is 1 and the force is 3, so anti-clockwise we've got 3 times 1. So again, clockwise is positive, anti-clockwise is negative. We can work out what the resultant moment is, okay, so we've got 10 take 3, so it's 7 Newton meters, and because the answer is positive, it's 7 Newton meters in the clockwise direction. So that's the resultant moment for this situation. Right, in a minute, and I will send you this slide as part of the task as well, what I'd like you to do is I'd like you to have a go at this question. Okay, so similar to the one we've just had, we've got a cruise ship is tethered to a dock at P. So P here is your point of pivot, that's where you're measuring from. The cruise ship is modelled as a rectangular laminar, so just like we've just modelled the previous one, PQRS, at P under the action of 3 coplanar forces. So we've got this 5,000 force, this 4,000 force, and this 6,000 force. Okay, A is the midpoint of PS. So if that's 240, that's 120, and it says B is the midpoint of RS. So so if that's 60, this distance is 30. Okay, and remember it's the distance when we're working out the moment, it's the distance to the axes of the force. So if that force acts in that direction, the distance to that force is just 30. These two will be at right angles, so it's just the magnitude of the force times the distance. This one though isn't at a right angle, so you'll have to use trigonometry or d sine theta to work out what the distance from, sorry, so you'll have to use trigonometry. I'm just trying to, so you'll have to use trigonometry to find the distance to that force. Now I'm just looking at it there, and I'll add this on the slide after. So if that acts in that direction, it'll act up here like that. So the distance to the force would be this bit here. Oh, and if we know that's 50, we can use the same thing, that this angle here is 50, and so we'd still get d sine 50. Okay, so you can work that out from there. This 5,000 force, 5,000 Newton force, okay, if we pull it up, we'll move it in the anti-clockwise direction, okay, if we pull it round, I should say, in the anti-clockwise direction. This force here would move it in the clockwise direction, and if you think about this force here, okay, because it's above P, if you're pulling it that way, it would move in the clockwise direction. So these two are clockwise and this is anti-clockwise. Have a go at that, okay, and I want you to send me your working out. Right, the next part that I want to just discuss with you is when we have moments in equilibrium. So when we have moments in equilibrium, okay, or when a rigid body is in equilibrium, the resultant force, so we need to think about forces as well on these, in any direction is 0 newtons, just like it always has been. And the resultant moment by any point is also 0 newton meters. So we can simplify many problems involving rigid bodies by choosing which points to take moments about. So when you are taking moments at a given point, you can ignore the rotational forces, rotational effect of any forces acting at that particular point, okay? So another little hint, if the resultant moment is 0, then the sum of the clockwise equals the sum of the anti-clockwise, because clockwise subtract anti-clockwise would equal 0, so it would make them both equal. Alright, so the first example we're going to look at is this one. Sorry about the two things appeared on the screen. I've obviously not done my animations well. So the diagram shows a uniform rod. Now that word uniform actually does tell us some information. So what the word uniform means is that the weight of the rod actually acts in the middle of the rod. So if this is a 3 metre rod, the weight of the rod will act half of that, so 1.5 metres down, which we'll come to in a minute. Okay, so it's a uniform rod and it's got a weight of 20 newtons. Okay, it rests horizontally on supports at A and C. Okay, and we're told that A to C is 2 meters, C to B is 1 meter. So it wants us to calculate the reaction at each of the supports. So there's a different reaction at each of the supports. So if we start labeling now our directions and our forces that we have acting on this uniform rod, okay, this is what we're going to get. So we've got that's the uniform rod. We've got the reaction force at C, and we've also got the reaction force at A. So the one at A I'm going to call RA, okay, and the one at C I'm going to call RC. As I said before, because it's a uniform rod, the weight, that 20 newtons, will act 1.5 metres away. Sorry, ignore these for a second. 1.5 metres away from A. It'll act directly in the middle, and that's because it's a uniform rod. Okay, coming back to my arrows now. If I was to take moments from A, which will help me if I take moments from A, because the distance will be 0, so it'll kind of get rid of this RA, okay, which will help me along. Then if I was to take moments from A, okay, if I was to pull A round in this direction, the rod would travel, if you watch my cursor, like this, so it would travel anti-clockwise. If I was to have this force here and think about the effect of that force RC, if I was to kind of pull it up, that would also act in the anti-clockwise direction, okay? And then my 20 Newton force, so if I was to pull the rod down from the middle, that would act in this direction, which is a clockwise force. Hopefully that arrow will appear in a minute. Looking at the forces though, okay, because the forces are in equilibrium, we've got RA and RC, and because they're in equilibrium, we know that that RA plus RC would have to equal 20, okay? So that's for our forces, and I'll come back to that in a minute. If we now look at our moments then, okay, and I'm taking my moments from A, okay, so now my arrows are starting to appear again. Okay, there's my third arrow, so that's going in the clockwise direction, and these two are going in the anti-clockwise direction. Okay, so if I take my moments now from A, okay, choose a pivot A, and A helps me, okay, because one of my distances is 0. So the clockwise moments is just the moment for this force, so the distance from A is 1.5 and the force is 20 newtons, so I've got 1.5 times 20, okay. In the anti-clockwise direction, the moment of this, the moment here, sorry, at A, is 0 for the distance times the force RA, and then the moment here at C is going to be 2 for the distance times RC, which helps us because this 0 times RA will disappear. So because we know they're in equilibrium now, we know clockwise is equal to anti-clockwise, so what we get is 30 for the clockwise is equal to 2 RC, okay? And so we can use that to find out what RC is. So that tells us if 30 is equal to 2 RC, then RC must be equal to 15. And then going back to this equation now to do with the forces, if RC is equal to 15, then that means that RA would have to be equal to 5 because they add up to give me 20. Okay. Sometimes these might lead to, say, 2 simultaneous equations that you then have to solve. Okay, last example I'm going to talk through. The answer's on there, just ignore that and I'll show you how we get there. Okay, so again, we've got a uniform beam. Okay, so this time it's a beam. AB, so A to B. It's got a mass of 40 kilograms, so remember the weight would be 40g, and a length of 5. So the fact that it's uniform and it has a length 5, that that weight 40g will act directly in the middle. Okay, so it'll act 2.5 meters across that beam. Okay, it rests on horizontal supports at C and at D. And okay, and it says when a man of mass 80 kilograms stands at E, when a man of mass stands on the beam at E, the magnitude of the reaction at D, so here, is twice the magnitude of the reaction at C. So if the reaction here is R, the reaction here is going to be 2R. It says by modelling the rod beam as a rod and the man as a particle, find the distance A to E. Okay, so you can see what the answer is, but let's just show how we get there. So again, if we label our forces and our directions on this diagram, okay, we've got, because it says that the reaction at D is twice the reaction at C, we've got that the reaction at D is R, and we've got the reaction at D will be 2R. Okay, again, as I said, in the middle now, okay, so at 2.5 metres across, we've got a weight of 40 G newtons, and the weight of the man is 80 G newtons, so they'll appear in a minute. The weight of the beam is halfway across, so that's 2.5 metres. The weight of the man is what we don't know, it's X metres across, but as I said, we've got 40 G and 80 G newtons. So now, if we start to consider the forces, okay, for the forces, we've got R plus 2R has to be equal to 40G plus 80G because they're in equilibrium. So we've got R plus 2R is 120G. Simplifying that, 3R is 120G. So that directly then tells us that R is 40G. Okay, so that gives us one of our unknowns straight away. If we now start to consider the moments, and again I'm going to do this from A, okay, so think about the directions now. So if I think about from A, so if I had this reaction force here, okay, this would be an anti-clockwise. So if I imagine I'm pulling it up and thinking about where it would go, it would give me an anti-clockwise movement, okay, in that direction. And the 2R as well, if I was to do the same thing there, it would give me an anti-clockwise movement. If I was to pull down on that beam though, okay, then that would move me in this direction. So both this 40G and 80G force would move me in this direction. So they are sorry, from A. So if I was to pull down on from A and think about the rotational effect, okay, it would move me, the beam would move in this direction, so it would move, so watch my cursor, it would go from being like that, to being like that, to being like that, so it's moving in a clockwise direction, so both of those are in a clockwise direction. Okay, so what we've got here, considering these forces, is in the clockwise direction, we've got 2.5 times 40G, for that 40G force, and we've got X times 80G for the force of the weight of the man, okay? So I've just highlighted the X in red to show it's X metres. Anti-clockwise, we've got 1 times R for the force, reaction force at C, and then for the reaction force at D, because it's 5 metres, I know that the distance from A to D has to be 4 metres, and I know the reaction force is 2, so I've got 1 times R plus 4 times 2R for my anti-clockwise direction. So because now I know that they are equal, okay, that gives me 100G plus 80xg has to be equal to R plus 8R. So simplifying that, I've got 100G plus 80xg is equal to 9R. Don't forget that I know what R is. Sorry, the menu's just appearing. I know that R is 40G. So if I've got 9R, that's going to give me 360G. Okay, so if I rearrange this now, 100G plus 80xg equals 360G. I've got 360G minus 100G divided by 80G, and if I do that, all the G's cancel out. I end up with 260 over 80, 26 over 8, 13 over 4, so it's 3.25 metres. Okay. The next part of the task that I'd like you to do is I'd like you to have a go at these questions. Okay, so again, they're uniform rods. You've been given the weights. C and D are in different places, and you need to find the magnitudes of the reactions at C and D for that one. And for question 2, in each of these diagrams, it's a light rod. So there is no, you can assume there is no weight because it says it's a light rod, but it does say it's in equilibrium. Okay, and again, I want you to find out what the missing values X and Y are. Okay, just email me with any problems and I'll help you try and work through that if I can.